Hello students. So today we are going to start the most important lecture. But as students who are following this lecture series, they know the initial is just a brief keyword I'm going for the day. So today's target is so that we can connect the dots. Okay, once you are able to connect the dots between topics, this group theory part or abstract algebra part becomes easy for you guys. Okay, so today's target will be the number one is conjugate elements in a group. Okay, from here I will go conjugacy is an equivalence relation. You are advised to have patience and try to connect these things, try to learn how to connect these things. Once we have proved that some relation is an equivalence relation on some set, then it's our duty or we are able to partition that set. Let's say conjugacy is an equivalence relation on group G, as we are studying about groups. So obviously we will be talking about group structures. Okay. Then as conjugacy is an equivalence relation, so we will have conjugacy classes for elements. Okay, like conjugacy class of A, conjugacy class of B, and so on, where A, B, those are elements coming from your group G. If this relation is an equivalence relation, then this partitions the group structure. Partition means, please notice this point, everything will be clear. Some classes or some particular groups partition something, it means those groups has no intersection or they have no element in common, and union of those classes gives the whole set G. This is the definition of here, not A and B only. This is true for any two classes. Okay, mutually they are disjoint, you can say. So if G is partitioned like this, then we will be discussing about if G is finite, then this is a very important point. We will move through this point to class equation. Okay. Then order of G will be nothing but number of elements in each conjugacy class. Fine. Now, after this, we will introduce the concept of normalizer of some element. And that will be represented by NA. Let's say you want normalizer of the element A, then that will be represented by NA. But fine. We will see how NA is a subgroup. After this, we will be discussing about some questions. Very important questions for UPSC. You can check your PYQs also. How questions are being asked from the class equation itself. There will be two types of questions from here. Number right, first is writing class equation for any particular group. Like they may ask, write the class equation for the group S3, write the class equation for the group Z8 and all. In the other type of questions, you may have a question like, so that a group of order p square where p is prime is always abelian. Such questions you may have. Or if a group is p group means group of order is p raised to the power n, then center of this group is always non-trivial, means it will consist some elements other than the identity element. Classify a group of order p cube. You getting my point? Let's say you have been given a question like, what is the order of the center of a group of order 121? So 121 means 11 square. 11 is a prime number. Means he wants to know order of the center of a group of order 11 square. You know p square is always abelian and center of an abelian group is equal to the group itself. So order of ZZ of order 121 will be also 121. Is that clear? So this is the overall picture for the first half of this lecture. Very much important, I am saying, for your CSE as well as IFS. People may think, sir, you should at least start some topic. We will connect this thing. We would have been connected these things. I know, because I was also a student earlier. No, each time we study separate topics and end of the day we think normalizer of A is coming from conjugacy class or conjugacy class is coming from NA. What is the difference between NA and ZZ? You getting my point? So that is why I drew a picture. Please take a screenshot of this picture. It will be like a path breaking or path showing for you guys. Whenever you have something to mind map, you can see this picture. Okay. So let's start now. So write the definition. Number first, conjugate elements. Obviously, you will have a group first. Let G comma star be a group. Okay. A is some element of Z. Then B belongs to G, means the element B is said to be conjugate to A. Please notice this point. An element will be conjugate to some element. Okay. If there exists some element X in G such that B can be written as X inverse AX, means please listen, if you want to show that some element B is conjugate to A, then you need to find some element X in G such that B can be represented by X inverse AX. There may be one element, two element, and so on. Some means at least one element you have to show existence of that element. Is that clear? Okay. Now, for example, find conjugate elements in Z6 to the element, let's say 5 in Z6, obviously means your A is 5 here. Okay dear, you want to know whether 1 can be written as x inverse 5x for some x belongs to Z6 or not. If this is possible, we will say 1 is conjugate to 5. If not possible, we will say 1 is not conjugate to 5. Is that clear? Okay. Let's change the color so that it will be more clear. Since, देखिए how to think. Since Z8 is an abelian group, this implies AB is equal to BA for all A and B in Z8. Getting? This implies B inverse is equal to BA B inverse, and this implies AB. So B inverse is identity, it goes to BA B inverse. This implies A equals BA B inverse. This implies A is conjugate to A. Check it out. From this relation, there exists some element B in Z8 such that A equals BA B inverse. So A is conjugate to. This is the conjugation relation, representation. Means if you have Z as an abelian group, then in that case, each element will be self-conjugate only. No two different element, like if I write by as x inverse ax, means by is conjugate to A, where y not equals to A. In that case, what can happen? xy will be equal to ax, whereas if G is abelian, then ax must be equal to xa or xy must be equal to yx. Means, note it down, it is your exam point. So question is answered in single minute only, but I wanted to detail the things in general. If G is abelian, then abelian group, obviously each element is self conjugate, you can say. Okay, so this is the point for you. Again, you must remember this point. If G is non-abelian, then only possibility for conjugate to some element is the element itself. Fine, let's move for the next. Now let's take some non-abelian group. Let us take the group as S3. Obviously the composition is composition of functions. Find conjugate elements to every, or you can say each element of S3. This is your question. So now we on the board. What is your S3, dear? S3 is I, sigma 1, sigma 2, sigma 3. People who are new in the lecture, for them I am writing, this means every element is image to itself. This is 1, 2, this is 2, 3, this is 1, 3, this is 1, 2, 3, and that is 1, 3, 2. Okay. Now, if I want to write what is the conjugate of sigma 1, So conjugate of sigma 1, let's say. For this, what I will check? See, I want to know is does there exist, please be on the board, some element x in S3 such that ki x inverse sigma 1x is some element by of S3. This I want to check. So for this to check, what I'm gonna do is I will write these expressions for all x. Getting? That means what I'm gonna do is, let's write I inverse sigma 1 I, sigma 1 inverse sigma 1 sigma 1, sigma 2 inverse sigma 1 sigma 2, sigma 3 inverse sigma 1 sigma 3, tau 1 inverse sigma 1 tau 1, and tau 2 inverse sigma 1. You getting my point? I will compose this thing. Obviously, this will be coming for sigma 1 only. This will be sigma 1 inverse sigma 1 identity. So identity composition, sigma 1 is sigma 1 again. Sigma 2 inverse sigma 1 sigma 2. This I wish to check. So dear, sigma 2 ka inverse is sigma 2 only, sigma 1 sigma 2. Getting? So if you forget, although earlier I told you how to compose this thing, if you forget, still I will do for you. 2 3 1 2 2 3. I want to know what is the image of 1 here. So here 1 ka image 1, here 1 ka 2, here 2 ka 3. So here 1 ka 3. Here 2 ka image 3, here 3 ka 3, here 3 ka 2, and this is remaining 1. So what do you call 1 ka 3, 3 ka 1, that is sigma 3 only. Check it out. Getting? In the same fashion, since sigma 3 is self-inverse element in S3, we have already proved this thing. So sigma 3 inverse is same as sigma 3. This is going to be 1 3 1 2 1 3, and it is going to be 1 2. So you can calculate this thing and you will be getting sigma 2 only. If you are going to calculate tau 1 inverse tau sigma 1 tau 1, so what was the tau 1 inverse? That was tau 2. This is sigma 1 and this is tau 1. So what is tau 2? 1 3 2. What it is? Sigma 1 1 2, and what is sigma, tau 1 is 1 2 3. It's gonna be 1 2 3. So here 1 ka image 2, 2 ka 1, 1 ka 3. Here 2 ka 2 ka image 3, 3 ka 3, 3 ka 2, and this is gonna be, so 1 ka image 3, 3 ka 1, it is coming out as sigma 3. Now tau 2 inverse is tau 1, sigma 1 tau 2. It means 1 2 3 1 2 1 3 2. So it's gonna be यहाँ पर 1 का इमेज 3, 3 का 3, 3 का 1, 2 का इमेज 1, 1 का 2, 2 का 3, rest is 2, and this is sigma 2 only. So what happens here? Are you surprised? No? Check what? All these possibilities. What it is showing? Elements which are conjugate to sigma 1 are, what are those elements which are conjugate to sigma 1? Sigma 1 itself, sigma 2 and sigma 3. You getting my point? This clearly indicates, from here you can check it out, that if sigma 1 is conjugate to sigma 2, then obviously sigma 2 will be conjugate to sigma 1. How? Let's say sigma 1 conjugate to sigma 1, then obviously sigma 1 can be written as x inverse ax for some x. It can be written as x sigma 1 x inverse A, sorry, this is sigma 1 sigma 2. So x can be written as x inverse ka inverse, that is sigma 2. So what it is showing, sigma 2 can be written as for some element ka inverse sigma 1 into that element, means sigma 2 is conjugate to sigma 1. We will be studying equivalence relation. So one step I have already done, that is called symmetry. Getting? If A is conjugate to B, then B is also conjugate to A. How? Let us here. So in the same fashion, dear, if I want to say elements which are conjugate to sigma 2, the same set. Elements which are conjugate to sigma 3, the same set I am going to get. Means you can write all the elements which are conjugate to sigma i's are sigma 1, sigma 2, sigma 3. Is that clear? In the same manner, I can found elements conjugate to tau 1. Those will be tau 1 and tau 2 only. So tau 2 is conjugate to tau 1 and tau 1 is conjugate to. Is that clear? Any doubt here? To find conjugation. See, if you have, objective paper, then obviously this much exercise is not needed. But in case of UPSC CSE or IFS, you have subjective paper, you have to write the steps. So someone may ask कि write all those conjugate elements for some particular element in S3. I am very much sure in the coming years such questions will be prevalent in nature in your exam. So be ready for the shock. Getting? This is UPSC. In this 21 also, people were not ready ki in the numerical analysis they will ask such type of questions where graph will be moving suddenly up. You remember? So you must be prepared about the concepts first. PYQ will be dealt obviously. Okay? Now, I'm moving for the next part. Okay. Sorry. What I was trying to say is, if someone says find conjugate to someone, so by the definition you know if some element to conjugate to something, then it must be represented as for some element x inverse ax type. So what I did is I will find all those possible combinations, x inverse ax, y inverse ay, z inverse an, and so on. When I will be writing all those possible combinations, obviously I will have all those possibilities for conjugation. Getting? So this is for subjective. And for objective, if someone asks, so I will think directly, okay, what can be the option? Tau 1 can be or not? If tau 1 is not there, then tau 2 cannot be there. So simply I will say sigma 1, sigma 2, sigma 3. But in UPSC, I will have to write all these steps. And steps are following being, you just write all possible combinations of the type x inverse ax, getting, for each x of your group. Fine. Now, the other part of our class is conjugacy is an equivalence relation. Please do remember this thing, this statement. Okay? Although I can prove it just seconds only, no problem. See, if I want to prove some relation as an equivalence relation, so what we have to show? Reflexive, symmetric, transitive. Number first, reflexive means every element should be related to itself. So what is our relation? Conjugacy means we have to show A is conjugate to A. So since A can be written as A inverse A, so that means each element is conjugate to itself always. Or you can say A can be written as E inverse A, E. Any element X can be written as X in E inverse E. So each element is conjugate to itself in a group. So it is reflexive. Number second, transitive. अभी आपको बोला था कि if A is conjugate to B, then we have to show B is conjugate to A. So if A is conjugate to B, this implies there exists some X in your group such that A can be written as X inverse AX. So this will imply it can be written as X inverse. If I take X and sorry, I'll be taking XA as X inverse AX, and XA X inverse will be EAE. Ultimately XA X inverse as B it was. I'm sorry. B is X inverse AX. So this implies XB So X inverse का inverse B X inverse as X. The same thing, this is inverse of this thing. So what it shows, B is conjugate to A is conjugate to B. So this is transit. Oh sorry, ये क्या लिख दिया? Symmetric. Okay. Number third is transitive. Many people will say, sir got confused. Yes, इंसान है ना. We are not machines. Sometimes in the lecture it happens, no problem. So if transitive is what? If A is related to B and B is related to C, then we have to show A is related to C. So dear, if A is related to me means A conjugate to B, then B can be written as X inverse AX. If B is conjugate to C, then C must be written as by inverse B by. You getting my point? From here, check it out. I want to show now A is conjugate to C means I must be writing A equals some alpha inverse C by, that is our target in mind. So just I will use here. So I will just put B as X inverse AX using this B here. So what will happen? C will be by inverse. B is what? X inverse AX. Okay. And here is by. Since X, Y are elements of a group, so they will follow associativity. But I can write it is here by inverse X inverse A X by. So in a group, AB ka inverse is B inverse A inverse in general. So what will be by inverse A inverse is by X ka inverse. Is it? No. This will be XY inverse. Then only by inverse X inverse will be written here. So and this is X by. So what it is showing dear? C is conjugate to A. और since it is symmetric, so you can follow. यहाँ से भी आप start कर सकते थे. और you can see कि A can be written as some alpha inverse C alpha. This means A conjugate to C, and that is your target only. क्लियर? देख लीजिए प्लीज, वॉच इट क्लियरली. इफ एनी डाउट देन यू बी रेज योर वॉइस. ओके, चल. So the next point is fundamental theorem on equivalence relations. What is the statement of this theorem? It says that if R is an equivalence relation on some set G, here G may be a not needed group, it is for all, on some, then equivalence classes, please underline this word, partition G. Partition, I already told you, any two equivalence class will be disjoint and union of those disjoint classes will give you the whole set itself. Is that clear? Obviously it is true for finite order. Cardinality is finite. Is that clear to you all? Fine. So what is equivalence classes? Since R is an equivalence relation on G, so let's say B and D, those are related with A. Then what I will say, equivalence class of A will be A, B, D, because A will be related to itself only always. And if other elements, let's say there are 10 elements, those are also related to A, then those 10 elements will also come inside equivalence class of A. In the same fashion, this will be nothing but B ka equivalence class or D ka equivalence class, because for B, A is related to B, D is related to B, and with the equivalence relation, transitivity also follows. Getting my point? Ultimately, what this fundamental theorem says, that each equivalence relation partitions your set into equivalence classes. And what those equivalence classes are? Means elements which are related to some element, that so the equivalence class of that element will be this collection, for other element that collection, and so on. Is that clear? What we have, since we have already proved conjugacy is an equivalence relation on group G. So if conjugacy is an equivalence relation, it means this G will be partitioned in the form of conjugacy classes. You getting my point? When I started the lecture, told that. So what will happen? Ki Z will be partitioned by conjugacy classes. So conjugacy class of A, union conjugacy, let's say A1, A2, and conjugacy class of AN, where any conjugacy class represents a set where all those elements will be coming which are conjugate to A1, which are conjugate to, iska apna conjugacy class hoga, iska it will have its conjugacy class. Obviously any two conjugacy classes will have no element in common. This I told you, because if any element they have in common, let's say by here also, by here also, so by will come inside any one of that and other will be vanished. Getting my point? Fine. Okay. So how we are going to use it, that I'm going to tell you now. If you want to write, so just an example will make more clear this concept. Write class equation, or you can say class equation, that is nothing but writing in G as a partition of its conjugacy classes of the group S3. So what it ultimately wants to show, कि you need to show that what is order of G as, or you need to represent order of G as order of conjugacy class of A plus order of conjugacy class of B and plus order of conjugacy, suppose that A1, A2 you are writing AN. So this is called the class equation informally. Okay. The original class equation will be derived later after introducing the concept of normalizer, but we are traveling towards that. Okay, although some authors may classify it as first class equation or second class equation, that is a different concept. We will discuss that end of the lecture. Okay, so what is our G here? I, sigma 1, sigma 2, sigma 3, tau 1, tau 2. Acha, conjugacy class of identity element will be always a singleton set and will be containing only the identity element. Okay, because E can be written as E inverse, or E can be written as for any. So conjugate to identity element is the identity element itself only. We have already discussed what is the conjugacy class of sigma 1. That is same as conjugacy class of sigma 2. Just previously we have seen it. Sigma 3, and that is nothing but the set sigma 1, sigma 2, sigma 3. What is conjugacy class of tau 1? That is same as conjugacy class of tau 2, and that is a set that is containing tau 1 and tau 2 only. So what I can write here as order of G is nothing but order of conjugacy class of identity, okay, plus order of conjugacy class of any sigma I plus order of conjugacy class of any tau I. People write here first this and then this. So you may have iska order is always 1, iska order is always 2, and iska order always 3. Check it out. So S3 के पास कितना एलिमेंट? 6. So 1 plus 2 plus 3 is equal to 6. Getting? Or you can say S3 can be partitioned by conjugacy class of I union conjugacy class of sigma 1 union conjugacy class of tau 1. Is that clear to you all? Equivalence relation and all? Sure. Should I move forward? Now, our next target is finding order of conjugacy class of A for any arbitrary element A of any group G. It's not all about S3, Z8, any group you can have. And you want to know ki how many elements are in the conjugacy class of A, how many elements are conjugacy other element, and so on. For this to entertain, we need to study that is another definition you can say, normalizer of an element A of that group. Connecting the dots is very much necessary here. And have patience, at the end of this lecture you will have a clear-cut picture, because I have one. So normalizer of an element, definition बोल रहा हूं, is nothing but collection of all those elements of the group G which commutes with A. That's itself. Somewhere you can, some people call it as a stabilizer also. So I will be using normalizer. In different books you can have that concept, but the concept is normalizer of some element. note it here, mark a star here. I will write the definition of center of group also here, so that you people don't confuse in that. Just to remove that confusion, center of ग्रुप होता है, ठीक है, नॉर्मलाइजर ऑफ सम एलिमेंट होता है, सेंट्रलाइजर सॉरी नॉर्मलाइजर ऑफ एन एलिमेंट, सेंटर ऑफ द होल ग्रुप. क्लियर है अभी? सेंटर ऑफ द ग्रुप कंटेन्स ऑल दोज एलिमेंट्स ऑफ द ग्रुप which commute with every element of the group. This is the difference. So you people also note down this altogether, so that confusion may be vanished. So why we are studying normalizer here? That is my big question. Answer I already told you inside in the starting of this lecture, that normalizer of A will be used to find number of conjugate to A. Clear? Before that, I must be aware about normalizer also. What are the general things about normalizer? We first know about some general things of the normalizer. So from here you can see, number first, normalizer of A is always a subgroup of that group. If you want to check, you can use your one-step subgroup test and check. Since identity will be always in normalizer, chalo, I will tell you, because EA will be always as EA. So normalizer of A is non-empty, because one is to apply one-step subgroup test, we first have that set as non-empty. Clear? And the second step is, if A belongs to normalizer of A, comma B belongs to normalizer of A, this must imply AB inverse also in normalizer of A. If this thing happens, we are done. So for this, since A belongs to normalizer of A, it means, sorry, normalizer of A we are using, so I will use X and Y here. Okay? Is that clear or not? Should I remove? Because A already I have used, so I have just removed key X and Y. Let's take arbitrary element. So X in normalizer of A, then X must commute with X A. If Y in normalizer of A, then Y must commute with A. Now what I wish to have, कि X by inverse also belongs to NA, means I wish to have, see, people always afraid of doing proofs, but I am showing those are very much easy once you are clear about the definitions. So what we want to show here, X by inverse must commute with A. This you wish to show. Means you wish to have X by inverse A as AX by inverse. Using these two relations, you have to reach there only. Only one step needed. You getting my point? Chal. So that is dot for you. That one line you have to fill. Don't be always in the rattamar and all. Okay. Ultimately, what we have done is कि normalizer of A is always a subgroup of that group. Should I move? No. There is a theorem which will be used to get our desired result. That means relation between, how it is the theorem is, what about relation between normalizer of some element and conjugates to that element A only. This is the target for us. And the relation between these gives this theorem. Statement is, if you want to write, then you can write any conjugate. You are writing? Write the statement. Right. I will use that statement from here only. Two elements, write the statement. Two elements X and Y of the group G gives rise to the same right or left coset of normalizer of A in G if and only if Y, if and only if, see, there are two things. Sorry for the disturbance. Any two element gives rise to the same coset, that may be right or that may be left coset of A if those are right, if and only if X and Y, if and only if X and Y give rise to same conjugate to A. That is the statement for you guys. Just in mathematically, if you want to say normalizer of A, let's say coset of normalizer of A generated by X and normalizer of A generated by Y, these two cosets are same, and this will be if and only if X inverse AX is same as Y inverse AY. In the simple form, you can write such a statement, and do remember this statement for UPSC. What I said, if X and Y gives rise to same coset of NA, then X and Y will give same conjugate to A. Don't forget this thing. I'm talking about just A. That means a fixed element I have taken. Is that clear? So what will happen? From here, I can conclude, although proof is easy, but I am just trying to connect the things first. If this thing happens, then total number of cosets of Na, either left or right, in G will be equal to total number of elements conjugate to A. That is another form of this statement. You also need to remember this thing. Means if you want to know how many elements are there in the conjugacy class of Na of A, then you can find index of Na in G. Index of Na in G is nothing but order of that collection of all cosets, not order, number of elements, and it is nothing but index of Na in G is what? Order of G upon order of Na. This I told you in the previous lecture. So that means if normalizer of the element A gives rise to 5 cosets, then total number of elements conjugate to A will be 5. If number of cosets of Na in G are 10, then number of elements conjugate to A will be 10. Obviously, this whole story will be running for the finite order groups. You got my point or not? Chala. So what you can say, now we are coming towards the class equation. Here, if you want to prove this thing, it is very easy. You can look in the book also, or you can see x y inverse, agle step mein y inverse, y inverse. This is identity, and from here you can get that. Only 4 to 5 line proof is there. No one is going to ask because it is very much important to prove something, to do something. So this is the supporting stuff. Still, I will say, please go through the proof from the book only. Let's move towards the next thing. And what is that next thing? That is the class equation. You can say first class equation. What it says, the order of G is nothing but summation of IGNA. What it says, let's say order of G is index of normalizer of A1 plus index of normalizer of A2 plus index of normalizer of AN in G. Is it clear to you all? Why? Because we have already proved from the partition of the set that order of G is nothing but number of elements in CA1 plus number of elements in CA2 plus number of elements in CAN. And what I have done from the previous theorem, that number of elements in CA1 will be nothing but index of NA1 in G. Number of elements in CA2 will be nothing but equal to index of normalizer of A2 in G, and so on. Getting? So either this thing you can write or this thing you can write. That is called first class equation. Am I clear? Everyone? How you are gonna use it? You can take some group structures which are non-abelian also. Abelian mein nothing is there. Simply you can write each element is conjugate to itself. So uska class equation will be always like 1 plus 1 plus 1. Let's say n order का ग्रुप है तो उसका क्लास इक्वेशन कैसा बन जाएगा? क्लास इक्वेशन ऑफ एन abelian group of order n, because each element will be conjugate to itself only. Nothing, no other element can be conjugate to that. This already we have proved. Sometimes it is easy to calculate or it is easy to discuss about index of normalizers. Then in that case we use this thing. Is that clear? Sure. Now we are moving towards the second class equation, or in the general class equation, which we call it as class equation also. Some different authors use that thing. Please notice, or class equation in general, or otherwise some people call it as second class equation. See, दिस इज नथिंग बट, एक बार मैं लिख देता हूं, ऑर्डर ऑफ जी इज नथिंग बट ऑर्डर ऑफ सेंटर ऑफ जी प्लस index of all those elements of A where A does not belongs to ZG. Why I have written like this? Please be on the board. See, if a element A belongs to ZG, this implies AX equals XA for all elements of the group G. This implies A as XA, X inverse, or this implies A is self-conjugate. Is that clear? Means no other element is conjugate to A, but in case of non-abelian groups, there may be some element which are not in the center of the group. You getting my point? Because those elements which are in the center of the group, those are the self-conjugate. But apart from the other than these elements, some elements will be there for which the conjugacy class will have more than one element. For those elements, I will try to calculate the index. Let's say 3 elements. समझिए इस बात को. Let's say we have 3 elements as A1, A2, A3, which are in the center of G. So what I will have? A1 will be conjugate to A1, A2 will be conjugate to A2, A3 will be conjugate to A3. Is that clear or not? Everyone? Fine. Let's say A4 is not in the center of the group. Means we will have some A5 which will be conjugate to A4. Or there may be some A6, A7, A8 which are conjugate to A4. That means conjugacy class of A will be containing as A4, A5, A6, A7, let's say. You getting my point? To find all those elements which are conjugate to A4, what I will be doing is, I will be finding number of cosets of n A4 in G. That means index of n A4 in G. So how the class equation looks like? Number of elements in center of G, those are self conjugate. So you can write those, you can count those elements. Let's say center of Z के अंदर 5 elements आ गए. Remaining elements, for remaining elements we will find index of normalizer of each of those elements. Getting? And this is the class equation looks like. If you have any doubts, then do let me know in the comment box. I'll surely try to reply you guys. If you don't have doubt, then nothing to reply. Is that fine? Everyone? So whatever I have told you in words, if you think I have to prove something, this class equation and all, please write those words in your copy. That is the proof only. Now, what is the importance of class equation? UPSC, please do understand these concepts, otherwise you may face disaster in your exam. How to use the class equation, that is I'm going to tell you. There will be some 2-3 standard kind of categories. I will state all those things, although I will prove those things, but you'll have to remember the proof as well as the statement also. So number first theorem, that is before that theorem, just I told you, no, P group. So write the definition of P group. Simply I will say if a group is of order n, where n is some positive integer, then I will say this is positive integer, okay? Then I will say keep G is a P group. Let's say G is a group of order P or P square or P power 20. Then that group will be called a P group type. Okay. Second, center of a P group is always non-trivial. Do remember these things. Means center of a P group cannot be equal to the identity element only. It will have at least one element other than the identity. Do remember, very important. You want to prove it? Very much easy only. Let order of group is P. Okay? Let's say क्या? Order of identity element is always 1. That means, and by Lagrange theorem, order of any element of G will be dividing P. Order of element divides the group ka order. So only identity can be of order 1. If G is of order P and P is prime, so iske only divisors are 1 and P itself. That means possible order for any element in a group of order P are either 1 or P. So 1 ka to keval identity we will have, other elements will be of order P. Is that clear or not? Everyone? Now, what I wish to have, I want to show the center of a group of order P or P square or P cube is always non-trivial, means order of the center of the group will not be equal to 1. So it will be P or P square and so on, depending on the order of the group. Getting? So that is the hint for you. Next is, just I'm coming on the all total proof, but what I'm doing is I'm just trying to consolidate the things first, then the proof will be in one go. Let's say a group of order P square, then G is always abelian. That is very important. You may have this question in your CSE exams. A group of order P square is always abelian. So since order of G is P square, from class equation, for the proof, although the proof is written on your book, but still I will just give you a hint. Should I give? Okay. So for class equation, what I know, order of G as order of ZG plus order of, index summation of index of n normalizers where A is not in center. Okay, this is the thing for you. Now, it means from the class equation we have please have patience. Once it is done, everything will be clear. Since for a P group, please be on the board. Very easy proof only. Center of the group cannot be, order of the center of the group cannot be 1 because it is always non-trivial. That means possibility for order of ZG are either P or P square. Why this? Since ZG is a subgroup of G, इसलिए by Lagrange theorem, in your exam you have to write all those things, otherwise you won't be getting marks. Order of ZG, a divisor of P square. So divisor of P square are what? Either P or P square or 1. 1 already we have denied here. 1 cannot be the order of that center of the group. So that may be P or P square. Now we are going to classify case 1. When order of ZG is P. If order of ZG is P, then here the crux, please notice this. I will change the color. Order of normalizer of some element will be greater than P. What will be? Greater than P. This you can think about actually. Why? If center has some element, suppose at 5, then normalizer of some element, मतलब collection of these things, इस पूरे का summation, you can say indexing, where A not in Z. So center जो होगा, that will be always a subset of these collections. So subset means, please note down these words, you should write. Subset means order of that bigger group, bigger set will be always greater than order of this thing. So this is the equation 2. From 1 and 2, what we are going to get? Order of ZG is P. Have patience here, otherwise you may do blunder here. From 1 and 2, also we have used, since normalizer of A is again a subgroup of G, so order of normalizer must divide order of G. Means order of normalizer of some element will be also either 1P or P square. From here we have seen that order of normalizer must be greater than P. So not this, means order of normalizer of A will be P square if order of ZG is P. So normalizer of A contains P square element, ZG contain other P element, means total will be P square plus P element. जबकि ग्रुप का ऑर्डर क्या था? P square only. Means this contradicts. Means this is not possible. Is that clear? If not clear, then go back again and see the video. So what is case 2? Number first, non-trivial means order of ZG cannot be 1. Order of ZG P, we have checked the possibility and got the contradiction, means this is also not possible. So what the other possibility may be? Order of ZG as P square. If order of ZG is P square, means this is order of group, means ZG is equal to G. Sorry, means ZG equals G. This implies every element of G commutes with every element of G, and this implies G is abelian. I hope everything is clear now. Getting?